Hello, everyone, and welcome back to another episode of Pinnacle Academy. I'm Sannel Patel, the Director of Business Development and Marketing at Pinnacle Ozone Solutions and a chemical engineer. Today, we are diving into a critical part of ozone system design, and often one that gets kind of forgotten. It's the injection and mass transfer that we're talking about. Because a lot of the generator itself of the ozone is only like half the equation. In real time, there's other challenges. And one of those main challenges is to get the ozone into the water. And where this can actually take place, and someone who's actually been the global leader for decades, is Mazzei Injector Company. So joining me today, I have Erich, who's an engineer at Mazzei and an expert in injection design and a gas transfer. Hi, Erich. And then I also have Tom Steinke here with me, who works closely with customers on ozone injection systems and applications. So, gentlemen, thank you both for joining us today.
Thank you.
Thanks for having us.
Yeah, so let's jump in a little bit of the company background. Mazzei has been around for decades and it's been out for a long period of time. Well, it has a really strong reputation in fluid mixing and gas transfer. Tom, do you mind giving us a quick overview of Mazzei, how it started, and what the foundations or the focus has been over time?
Yes, so the company was founded in 1978 by Angelo Mazzei, and Angelo remains active, very active today in the business. Back in 78 in Bakersfield, California, where Angelo was living, studied Venturis there and applied a Venturi to agricultural fields that have irrigation water coming up from wells. And Venturi was allowing fertilizer and chemicals to be put into that water without breaking pressure. And so that was the first product that Mazzei had as a company. And from there, we branched off into many other markets, oil and gas, the wine industry, pulp and paper, and many others, including municipal water, drinking water, and municipal wastewater, which is what we're here talking about today. The products that we have do a good job of mixing any chemical or gas in with the water without breaking pressure, as I mentioned before. And then not only that, but introducing the chemical, but then mixing it very well downstream with the bulk flow, so that you're getting, if it's in the case of gas, good dissolution. If it's in the case of chemical, good mixing of the chemical, and you're getting that chemical or dissolved gas spread throughout the bulk flow. So you've got a nice consistent, in a very short period of time, a nice consistent water quality coming downstream of the system. And so that's where the company was founded, and that's still where the company is based today, with all of our manufacturing being done here in the United States.
Thank you so much. I didn't know that it was in it was started up in California and been there for all these years. So Mazzei is known for holding a lot of patents related to injection and mixing technology. Erich, from an engineering perspective, what are some of the key innovations behind those designs? What are the fundamentals that set Mazzei injectors apart from a normal Venturi versus a diffuser system?
Yeah, thanks, Now. That's a great question. So what I would start with probably by talking about is where they're similar. So, a Mazzei injector is, at the end of the day, a Venturi injector. So it's a convergent, divergent nozzle that utilizes the increase in velocity of a fluid to produce a static pressure drop in the injector to pull something in. It could be fertilizer, it could be air in a wine application, it could be ozone in a municipal drinking water application. So there are a lot of similarities from a mechanical standpoint. Where there would be what I would identify as key differences would be as follows. So first of all, these injectors are designed fit for purpose. They are intended for use in drinking water, reused water, wastewater, industrial process water applications. And what I mean by that is several things. First of all, they're designed to accommodate higher back pressure. We don't really design injectors to have optimal gas suction in a situation where there's very little back pressure, because very few times do we see zero back pressure applications, because in order to efficiently dissolve gases into water, you need some amount of static pressure in the mainline. Mm-hmm. So our injectors are designed to have optimal gas to liquid ratios in the kinds of back pressure, say maybe 12 feet to 30 or 40 feet, that are typical in drinking water and industrial water applications. And then going back to the gas to liquid ratio, I would say that is another place where we've designed fit for purpose. the goal here isn't necessarily to draw as much gas as we possibly can with as little motive flow as possible. That would be very energy efficient, for instance. But where you pay the price for that is, potential stratification between the gas and the water in the side stream, a dearth of mixing that would result in less efficient mass transfer within the side stream, and a number of different costs associated with that. On the flip side, you don't want too much water because then you're spending energy. That's energy consumption, pumping energy, without any gain in efficiency, with only marginal gain in efficiency. But, the important thing to understand is that it's not just the injector. We have this whole line of custom designed secondary mixing devices in the bulk flow, things like basin nozzle manifolds, things like pipeline flash reactors. And these, in addition to the injector, give us a second shot. They allow us to, when we go into the main line, re-shear those bubbles, again, increase the surface area, provide efficient mixing in order to distribute those ozone bubbles, increase the surface area and gas to liquid ratio and interface throughout the main line, and then get a second shot at the transfer. And, even in addition to those two devices, the secondary mixing device and the injector, we have a number of additional components that we bring to bear on these kinds of application challenges. Those include things like flash reactors, degas separators that perform work in the side stream. Or in the main line, we have things like gas dams that prevent crowned gas from drifting back upstream and potentially wreaking havoc in the case of ozone if it's on materials that aren't compatible. We utilize plate mixers to actually re-entrain crowned gas and give us a third shot mass transfer. So, it's all these kind of components that are out there that combine together into a system. And that's, I think, the last point that I want to make is to say that, not all intellectual property is captured in patents of the kind that you referred to. There are, apparatuses and there are methods. And we have a number of apparatuses, but the real magic is understanding how to put all those together into a single mass transfer dissolution system. You have to understand how and why to combine components and when to use one versus another one. And so a lot of that is, a kind of intangible. And we're equally proud of those developments. Our internal proprietary calculation engines, our decades of experience. And the thing that we're probably most proud of is hundreds of reference installations operating in the field, performing efficiently, demonstrating the value of our technology. So to summarize, there's a lot of similarities to typical Venturi injectors, but ours are really designed fit for a purpose and are just one component of an integrated mass transfer gas dissolution system.
I think that's the great thing about the mass transfer portion of it, right? I know that's one of the most important parameters is mass transfer efficiency. And if ozone is not dissolved efficiently, then you end up wasting a lot of energy and losing performance. So is this one of the reasons why Mazzei is able to achieve the high transfer efficiencies because of all that critical work that has been done on ozone applications?
Oh, yeah. Yeah, that definitely, factors into it as the experience and, our proprietary modeling and all that. I'd say it's very important as well. And I'd give you kind of an example as to why mass transfer efficiency is something that we focus on as keenly as we do. We have a lot of different applications and some very small plants and some very large ones. And a great example is the Wiley Water Treatment Plant in Texas. This is the crown jewel of the North Texas Municipal Water District. This is a plant that draws water as much as 900 million gallons a day out of Lake Lavon in North Texas, primarily treating it for taste and odor, geosmin and MIB during algal events in the lake. And with that kind of flow, they need about a 3.5 milligram per liter dose of ozone at peak. And so when these guys are operating in peak condition, that's 25,000 pounds of ozone per day that they're producing, and they tend to produce at 12% weight. And so that's, 220,000 pounds per day of oxygen. And those things both have cost. The ozone in terms of the specific energy in the ozone generator necessary to produce the ozone, and the oxygen in terms of the cost that you're paying, because for an application that size, you're almost always utilizing a purchased liquid oxygen. And so now we've got to make some assumptions in order to kind of quantify this from a cost standpoint. So if we say that, a typical ozone generator using an application like Wiley will have a specific energy requirement of about 3.5 kilowatt hours per pound of ozone produced, and we say that, you've got maybe a 10 cent per kilowatt hour energy cost, and then say that we have, 10 cents per pound of oxygen. And, it's important to note that oxygen is highly variable around the country. There are places out west where we're seeing 3 times that. But, I'd rather be conservative about this estimate rather than, be exaggerating about it. But if you take all those things together and look at just the consumables cost to produce the ozone, the specific energy in the generator and the oxygen in the generator, at Wiley, that's going to run up to, $25,000 per day. And so if we take that and extrapolate that across a year and really look at the numbers there, what that translates into is that every percentage of mass transfer that is gained or lost in terms of efficiency, that translates into, $90,000 a year for a single percentage change. So for 2%, $180,000 a year, 3%, $270,000 a year. I mean, that's real money. That's enough for potentially hiring additional plant operators. It's a lot of value tied up in what appears at the outset to be fairly incremental increases in performance. And look, we all know that municipal budgets are tight and that savings are important. And, efficient mass transfer is one of those places that we feel like is, low-hanging fruit. But to kind of go back from the why we focus on it so much to the how we go about it, I would say, again, I'd leverage our decades of experience designing and refining these systems across time. I would say the effective use of our tools, not just the components that we sell, but things like computational fluid dynamics, which have helped us really dive into the relationships in between efficient mixing and uniformity in the mainline and how that relates to mass transfer. I refer to our proprietary calc engines that really don't just look at solubility, but take the specific applications in hand. We're going to treat a taste and odor application with geosmin and MIB very differently than we would treat an application that's also taste and odor with hydrogen sulfide, where the reaction rate kinetics are very different. We do look at solubility, with respect to water pressure, temperature, gas concentration, and we combine all of those things in order to construct a custom designed system for every ozone application. And there's, a lot of different tricks that we can employ. In high dose applications, we can put multiple mainline mixing devices in series to break up the dose. Sometimes we do that in order to keep the dissolved residual low to prevent the formation of bromate in applications where bromate formation is a risk. So, again, the way that we're able to focus on this as much as we are is by making sure that we're designing a custom system fit for the application in question rather than some sort of one-size-fits-all solution.
So I know we talking here about system integration. I just want to take a step back a little bit and talk about the physics. Mazzei injectors are based off the Venturi principles and using pressure differential to draw gas into a water stream. Erich, do you mind just walking us through what actually happens inside the Venturi so our audience gets an understanding about how pressure drops and velocity profiles actually allow the ozone gas to be pulled in and mix efficiently? I think that's the main thing that our audience would like to hear.
Yeah, absolutely. I think it's important to do what you're asking, Sannel. I think it's important to go back to the fundamentals. This is something that I tell my application engineers all the time when we're working on projects. So the bite-sized answer here is that, like you indicated, the Venturi injector is a function of Venturi effect, originally identified by the scientist Giovanni Venturi in the mid-18th century. And it's essentially an embodiment of a different principle, the Bernoulli principle that was identified by Daniel. And even that is just essentially, at the end of the day, a restatement of the conservation of energy principle. So what we're talking about here is in the closed system of an injector, as the nozzle converges, that is going to cause an increase in velocity. And you have the same mass of water that is increased in velocity. And as a result, there is more energy in that system. And because this is a closed system, that energy has to have come from somewhere. And so it turns out that energy comes from a drop in static pressure right there at the throat of the injector. And it's that drop in static pressure, that conversion of the potential energy of the static pressure into the kinetic energy of the flowing fluid in the injector throat that really serves to do the work of the injector. And that is lifting fluids in the fertilizer applications that Tom referred to, or suctioning gas in the gas applications. So it's important to note, or it's worth noting, I guess, that exact relationship in the equation that defines it. It's called the Bernoulli equation. It was actually discovered and developed by Leonard Euler. But this is one of those things where if we named every equation that Leonard Euler first developed after him, they'd all be called the Euler equation. So this one went to Bernoulli. And the other thing I'd note is that, from a scientific mechanics standpoint, is the injector really does function like an orifice. So a good comparison to it would be like an orifice plate that you see on the oxygen side of an ozone system that is used to calibrate the thermal mass flow meters on the ozone generators. And the reason that's important is that we can look at the pressure drop and by this Bernoulli equation, understand what the flow through the orifice is. And that relationship that's defined by that equation is how, for instance, Venturi flow meters work. What I would add to this from our specific standpoint is to say that what Giovanni Venturi identified and what Daniel Bernoulli described is something that I like to think of as Angelo Mazzei having perfected, which is that, again, like I was discussing earlier, we've optimized these to ensure that unlike the orifice plate that's used in an orifice plate flow meter on an oxygen system, we're not losing a lot of energy to friction or to heat or something like that. We're making sure that energy conversion is as clean as it possibly can so we can develop as much suction as we possibly can from a given flow of fluid. And again, balanced in a certain way so as not to have too much suction and reduce gas to liquid ratios and mixing in the side stream unacceptably, not to have too little suction so that we're using too much energy in order to promote this side stream mixing. It's really kind of like a Goldilocks engineered solution. And then, of course, when you take that and combine that with those secondary mixing devices, that's where you get the complete system.
Yeah, so there's definitely a lot more science than our audience knows about. But yeah, thank you so much for sharing that. Going into more of the system integration, I know at Pinnacle, we don't treat ozone generators or injectors as two separate components. We kind of design everything as a complete system because they all have to work together. It may be the oxygen concentrator, the ozone generator, injection or mixing systems, off-gassing, or even contact systems. And that's where Mazzei plays a critical role in introducing that ozone into the water, right, into mixing it. Tom, can you walk us through how Mazzei actually goes about this approach, how we go about selecting the right injector based on flow and pressure, integrating the Venturi onto an overall injection skid, and then any type of connections downstream as well, like a flash reactor or even like a basin manifold? Can you tell us a little bit about how it's properly designed and how they all work together?
So as Erich was describing with the Venturi, the first step of that, the primary mixing step, is to get the ozone gas into the water. And that's looking at the operating parameters of the Venturi and the amount of ozone that needs to be drawn into the system through the side stream is used to do the first step in selection of the Venturi sizing. But from there, there's a lot more that comes to play in how the Venturi itself interacts with the downstream system, and that's the secondary mixing device. So the Venturi is on a side stream. And we're introducing the ozone in the side stream to create the conditions to draw the suction that's required through the Venturi. But then we need to take that side stream that's got dissolved ozone in it and has undissolved ozone in it and introduce that side stream into the bulk flow. And that's what we do through the secondary mixing devices. Those can be the pipeline flash reactor or the basin nozzle manifold. And the two are really educated by each other. So the design of the basin nozzle manifold is in conjunction with what the Venturi is pulling through. So, or the pipeline flash reactor is educated by the Venturi flows. And those so they're working in connection. Now, there's several variables there that are involved in working through that design to make sure that the two sync together and that they operate the way they're supposed to operate. And that comes into play some additional variables that need to be taken into account, such as the design parameters of the water plant, the water depth of the water, the temperature of the water, the components that we're oxidizing, what their reaction rates are, what the decay curves are in the ozone, so we know how quickly the ozone, once it's in the water, how quickly the ozone goes away and reacts with the components. So there's a whole set of variables then, once we've got the design on the primary and secondary device, that we need to take into account of the water treatment plant to make sure that once the side stream is introduced into the bulk flow, that we're getting the mass transfer efficiencies that we want to see. It's reacting with the water, providing a nice even mix, as I mentioned before, so that the ozone is doing the work that it's designed to do. And so those variables are taken into account, as well as the variables of the secondary mixing device in itself. So the secondary mixing device will have nozzles that provide a certain thrust and energies into the bulk flow, and that's where we're getting our mixing energy. That is educated from the computational fluid dynamics modeling that we do, as well as our proprietary calculation engines that Erich had mentioned, which is all derived from the hundreds of installations we have and the decades of experience that we have in applying the system. So the calculation engines and the CFD models are calibrated with historical data. So, as we know, if you've got a modeling system or some kind of fancy tools that we have these days, if they're not calibrated properly, garbage in, garbage out. So those are all calibrated with the experience that we have. And then we are able then to analyze all of those variables, not only on the primary mixing system, the secondary mixing system, how the water being introduced to the secondary mixing system is mixing with the bulk flow, understanding what the reaction rates are, how that ozone is transferring into the water to get transfer efficiencies that are targeted by the plant to generate the efficiencies that Erich was mentioning before, allows us to look at all the variables that we understand in our systems, the variables associated with the plant design, and the variables associated with how the components, the secondary mixing devices are put into the system to work in conjunction to provide the transfer efficiencies that the consulting engineer is looking for, making sure that the ozone is actually going to do the work that it's designed to do in the system. So that's fairly complex the deeper you get into it. But through the tools that we have and the experience that we have, we're able to monitor all those variables, understand them, and produce the desired product, which is a complete system.
So there's definitely a lot of things that need to be taken into consideration. So kind of building on that from your perspective, how important is the collaboration between Mazzei and Pinnacle during the design phase, not even before we get to the point where we're selling a system, during the design phase, specifically with the ozone generator and the injector, help assure that the entire system is designed to be optimized and not just separate components? How would you, from your perspective, help understand how important that phase is?
So the priority of that, the importance of that can't be understated. So for the end user, the consulting engineer and the end user, Pinnacle and Mazzei have to work together as a team seamlessly so that there is no differentiation between what the ozone generator is doing and what the ozone dissolution system is doing, because the consulting engineer is designing a system where the ozone needs to do its work, and the end user is paying for that very same system. So the two of us working together is very, very important in that design phase. And in that design phase, it's not only the two of us working together, it's the conversations that we're both having with the consulting engineer. Many times the three of us will be on the phone together, working through the problems. Sometimes there's specific things associated with the dissolution system where I'm answering questions that the consulting engineer has. Well, on your end, Pinnacle is doing the exact same thing on their design. And then it's coming together to make sure that it is a complete system, that we do partner together, and that it is completely seamless. So one of the advantages that we have in having those long-term discussions is that we can understand where the weaknesses and strengths are of each of our individual systems. So there are many projects that we've worked on in the past where an ozone generator, given its setup, needs to reduce its ozone gas concentration that is being provided to the mixing system. Ozone gas concentration reduction negatively impacts our transfer efficiency. So there are times that we can save and prevent going to a next larger ozone generator by allowing the generator to operate with a lower ozone gas concentration. We can tweak our system because we understand all those variables, because we have the CFD modeling tools, because we have the mass calculation engines that have all been calibrated. We can tweak those, understand what the tweaks mean to our system, and say, yeah, we can do this, or yeah, we can do that, but the compromise is we've got to do X, Y, and Z in terms of the design. So coming up with a system that will allow the ozone generator to produce under its full mode without necessarily going to the next size, while still maintaining the performance efficiencies that we see with the transfer efficiency system. And it's reversed. There are times where we have weaknesses on the transfer efficiency system, and we go back to Pinnacle and say, hey, is it possible under these conditions that you can provide us a higher ozone gas concentration? The higher ozone gas concentration allows our system not to work as hard and still provide the efficiency that the consulting engineer is looking for. So that kind of collaboration is not only very important, but it's vital in order to have a successful project.
And I know we always say this, we say every single water sample is different, every single system that's out there is different. Every system performs differently on paper than on field, right? Field and paper sometimes doesn't actually work together that we think of. So Eric, what are some of the most common mistakes that engineers make when designing ozone injection systems? And to add to that question is what happens when an injector is improperly sized or operates under different design conditions? What are the effects that we can see?
I'd probably frame it a little bit differently and, kind of go back to Tom's last answer a little bit, which is to say that, I don't know if I would say that we're talking about mistakes that the consulting engineers are making so much as that these projects are, continuously evolving. You might have had an ozone system design that was done preliminarily as part of a basis of design report or something like that. And then, at a later stage, as it starts to move forward, and this is particularly true of projects that utilize innovative procurement methods, things like construction manager, risk, progressive design and build, and other kind of delivery methods along those lines that are continuously evolving. So, the design team might circle back and might do some bench testing, might do some piloting, and determine that they need a higher ozone dose. And I want to expand a little bit on what Tom was talking about in terms of gas concentration. And the reason that we're both bringing this up is this is something that does happen quite commonly, is that we'll have a situation where they decide that they need a bigger ozone generator, but maybe the ozone building is already kind of footprinted out, it's already designed, or there's a limited amount of power that the site can get, or something that constrains the ability to increase the size of the ozone generators. And the flexibility that Tom was referring to earlier is true of all ozone generators. They can operate in a pretty wide range, assuming a constant feed gas, liquid oxygen, or an oxygen concentrator with a somewhat lower purity, assuming a continuous, consistent cooling water supply. There's a lot of variability. The two boundaries that you operate with an ozone generator are, at a certain point, if you're flowing too much gas through the ozone generator, you're going to end up compressing the gas and changing the gas density, and that will shift you on the Paschen curve and result in a higher voltage necessary in order to achieve that breakdown voltage that produces the plasma that converts oxygen to ozone. So that's one boundary. Another boundary is power. Past a certain point, you can only apply so much power to the ozone dielectric before you start, getting diminishing returns, as that extra power isn't converted into additional molecular energy that results in ozone production. It's just converted to heat, which actually tends to degrade ozone. So those are the boundary conditions. But within those boundaries, there's a wide variety of different production ranges and different gas concentrations that are available. And so like Tom was saying, because of that, it's always very easy, or it's often very easy for the ozone generator manufacturer to say, hey, I can't give you the new production that you need for your new dose at 10% weight, but I can do it at 8% weight. And that's fine. Like Tom suggested, those changes are something that we can absolutely accommodate. But it is important to understand that that kind of a change negatively impacts the dissolution system, really in three ways. First of all, you're talking about just a higher volume of gas. And as a result of that, we might need more suction. So that might mean changes to the elevation of the injector for, hydrostatic head differential. That could mean, increasing the side stream pump size in order to increase the differential that way to produce more gas suction. And even if we're not there, even if we have some headroom on injector suction, like Tom suggested, that just increased the gas to liquid ratio, which has a negative impact potentially on mixing, on stratification in the side stream, and so on. And then the third way that it hits, of course, is Henry's law. A lower gas concentration equates to lower partial pressure, and lower partial pressure equates to lower solubility. So as a result of that, we're going to have a lower solubility cap and have a harder time transferring as much of that gas in the side stream, making us more reliant on the main one. And again, I want to reemphasize the point that these are all things that can be accommodated. But to go back to the last question, that's why it's so important for all of us, the design build team, the ozone system suppliers such as Pinnacle, the Mazzei Injector Company, to work together as a single team so that those kinds of changes and those kinds of challenges are understood early by us, and we can communicate what, if any, trade-offs in terms of mass transfer efficiency, pumping energy, that sort of thing, are going to be necessary in order to accommodate the new design of the new system. So, that's one example. Another example of change that can occur over time is a hydraulic head in the plant. We've seen plants that were originally planning on having ozone contactors with about 20 feet of head reduced down to as little as 2 feet of head because of changes totally unrelated to the ozone system. And of course, 2 feet of pressure head is very, very difficult. You get very large bubbles. They're very buoyant. They crown very, very quickly. Certainly from a pressure standpoint, again, going back to Henry's law, mass transfer efficiency becomes very difficult in that circumstance. We've seen it the other way. We've seen 20 feet become 40 or 50 or even 60 feet of pressure head in contact. And from a mass transfer standpoint, that's fantastic. That it really helps make the system efficient. Where that hurts is that increased back pressure is without some kind of change to the inlet pressure or the elevations or something like that on the system, going to result in less of a differential around the injector, and that's going to create potentially suction challenges that require more energy and more motive water flow. So again, I wouldn't say it's about mistakes. It's just important that as these projects are developing, particularly with these innovative delivery methods, that communication lines remain clear and remain in communication with everybody and informed throughout the entire process so that when we make these changes, we can understand the full impact of those changes rather than, understanding, hey, this is great for the ozone generation system without realizing that there are attendant trade-offs associated with the dissolution system.
And I know you gave an example about, Eric, the Texas facility that does the drinking water application and treats for geosm. But touching with Tom, I did want to ask you, can you share an example of a project? I know there's a wide range of different projects that you guys work with, like applications are like municipal drinking water, industrial reuse, aquaculture, and even agriculture. Are there any different projects or significant projects or like system specifications that may change these? Could you just give us an example of certain projects in these applications?
We've got actually several installations in the city of Orlando, Florida, for Orlando Utilities Commission. They have 7 or 8 water treatment plants that are all operating on wells. And more than 20 years ago, they put in ozone to treat hydrogen sulfide using fine bubble diffusion. And we're in the process right now of retrofitting all of those fine bubble diffusers into side stream injection systems. We've done 3 plants. We're currently just bid a 4th. And some of the advantages that they saw, initially they were switching over from fine bubble diffusion due to the maintenance and enclosed entry spaces tied to the fine bubble diffusers. After installation, we started looking at some of the data that they were generating out of their plants, and we started seeing 20 to 30% reduction in the amount of liquid oxygen that was being used, a 20-30% reduction in the amount of ozone that was being generated and produced to treat the same flows. We compared that data from year to year on very similar flows and very similar water qualities. We attribute it to a couple of items that because you get complete mixing immediately, as opposed to a fine bubble diffuser that has passive mixing, the ozone dissolves into the water very quickly, and you're able to take a dissolved ozone residual very shortly downstream of where we're introducing the ozone into the bulk flow. And that provides a signal that's relatively constant, and there is no hunting and pecking for the proper ozone dosage as was seen with the fine bubble diffusers. So the mixing, the efficiency, mass transfer efficiency, not only contributed to that savings, but in addition to a steady state signal coming out of the dissolved ozone residual, which allowed the operators to select their ozone residual more precisely, generating that savings. Another plant that we have is in Ontario, Mannheim Water Treatment Plant, where they similarly calculated that they could have a 40% savings in their maintenance costs by converting from fine bubble diffusion to side stream injection. And shortly after they converted to side stream injection, they started noticing a whole bunch of other advantages that they were seeing above and beyond the maintenance issues. For example, the total organic carbon being removed through the plant increased, and that increase then allowed them to decrease the amount of chlorine they were adding in their disinfection system, so savings there, as well as producing better water quality. They noticed that their filter backwash times increased in duration, which decreased the amount of backwash water they were generating, and other savings that they were seeing. And as they continued to study the plant, they continued to see further and further savings. It almost seems like every year they were stumbling across a different savings that they were tying to ozone.
Okay, so I guess this is a question that our audience loves to hear. What is the future, right? What is the future? Looking ahead, where do you see Mazzei technology evolving? Are there any new design materials or even different type of designs or performance improvements that Mazzei is currently working on? I'll start with Eric and then jump over to Tom.
Well, I'm glad your audience likes hearing the answer to that question, because I got to tell you, Sannel, that is a question I love answering. So I'm very, very glad that you asked that. I mean, what an exciting time to be in water treatment, water treatment technologies, right? We're seeing the advent of really mass scale, no longer experimental reuse water systems. We're identifying emerging contaminants that ozone and oxidation in general, in particular advanced oxidation, are very adept at dealing with. it seems like every day I'm reading about, some kind of new approach to water treatment. And so it's something that's very exciting to be a part of. And Mazzei absolutely is a part of that. So the first thing I'd probably mention, because it's fairly recent, is we've taken the skill that we've developed over decades of gas liquid applications and have applied it to a new liquid application. So we developed last year in 2025, patented a new device called the chemical mixing reactor, the CMR. And this is bringing to bear some of the successes that we've had on mainline mixing in the pipe with the pipeline flash reactor to a different kind of application. And this is a product that's already been sold into projects in Utah, Pennsylvania, South Carolina, a number of others pending. And what it really intends to do is work on the coagulant that is injected in the plant ahead of the floc set process. And so, the first application that we designed this around was the most challenging one that we've seen yet. This involved 0.075 gallons per minute of coagulant flow going into a main line flow of more than 23,000 gallons per minute. And the goal here was to achieve 80% uniformity between that solute and that solvent in a period of time of less than 3 seconds. And the 3 seconds is important because the particular chemical in question has a couple of different mechanisms and mechanics for flocculation. The first of those is charge neutralization that is most effective immediately after the chemical is introduced to the water. The chemical then undergoes some changes, becomes intermediate species before finally converting to a final species, whereupon the second mechanic, sweep flocculation, activates. And charge neutralization is a much, much more efficient mechanism for flocculation than sweep flocculation is. And as a result of that, if we can shift the balance of the flocculation action to the charge neutralization, we can potentially reduce the amount of chemical that's being used really kind of significantly. And that would be a hard enough challenge as it was with that sheer volume of solvent compared to the amount of solute. But we were given an additional challenge, which is the main tool that gets used in these kind of applications is pressure loss in things like static mixers and that sort of thing. But we were given an objective to meet a pressure loss in this device of under 0.15 psi. And it took a lot of different iterations to figure out how to put all of those things together. And I'm very fond of saying that the device that we eventually went to patent with was the first branching iteration of the 29th branch of the 8th branch of the 4th branch, a prototype that we called 4.H.29.1. So it took a lot of investigation, CFD, a lot of scientific work in order to finally develop that. But, that's a new technology as of last year that we are very proud of, very excited to get out into the market so people can see. We might have become well known for our aeration and our ozonation applications, but we really are kind of all things mixing. We're also branching out to other gas to liquid applications other than the standard 3 that we've done all these years of aeration, ozone, and pure oxygen. Relatively easy example of that is we just are now installing our first carbon dioxide dissolution application. And that's interesting. It's not particularly challenging. CO2 is very, very, very soluble in water, so that becomes much more of a mixing game than a dissolution game. But on the opposite side of that, we've looked at dissolving propane into water. And this is an emerging application where you're using propane for what's called co-metabolic biodegradation in conjunction with a biological filter for the reduction of 1,4-dioxane as an emerging contaminant. Propane is much, much less soluble than these other gases that we've been talking about. So it presents a particular challenge in order to dissolve that into solution and, deal with this emerging contaminant that doesn't have a lot of other great mainline treatment technologies. UV AOP is a good example of that, but that's pretty energy intensive. Another thing is these reuse water applications are causing us to continually up our game because the dosages on these, particularly now that we have DPR regulations in California that call for a 1-to-1 ratio of ozone to TOC, means that we're getting some very, very high applied ozone dosages, but that's not really downshifting the expectations on mass transfer efficiency that we certainly played a big role in setting. So we're having to up our game and figure out ways to achieve even higher ozone doses transferred efficiently than we've, really ever seen before. And the last point of innovation that I would note is, look, we recognize that side stream injection can be quite a bit more efficient than other technologies that are out there for gas dissolution. But there is an energy cost potentially associated, especially if you don't look at plant hydraulics and the need for deeper contact basins and diffusers and all that. And, the International Ozone Association Pan-American Group Municipal Committee looked at this in a 2018 paper and concluded that the cost of a side stream system, if you're kind of doing big numbers, adds something like a kilowatt hour per pound of ozone produced. And so if we were talking earlier about Wiley 3.5 kilowatt hours per pound, that's not an insignificant amount of energy consumption associated with side stream injection. And so part of what we're doing is we're innovating in terms of controls and in terms of control narratives and system operation and trying to figure out, one thing that's been done for years is to use VFDs to modulate side stream pump flow. In cases where you need less suction, turn the VFD down and get less flow, less suction, and some energy savings. But right now, that's being utilized in a static pre-programmed manner. So if the gas flow drops to here, drop the VFD to this, the gas flow increases, raise the VFD. And what we're looking at is potentially dynamic control narratives, things that look at factors such as gas to liquid ratio, such as minimum amounts of side stream fraction of mainline flow that we need to achieve efficient mixing in the bulk flow. Look at the available gas pressure so that maybe we don't have to do as much suction because we can utilize the compression of the gas from ozone generators that are capable of producing gas at high pressure to force that into the injector beyond what the native suction capacity of the injector would be, and to balance all of those variables in a narrative that allows the dynamic adjustment of the side stream pump flow rate to really strike a balance between energy consumption on the one hand and keep that as a minimum at all times, and then mass transfer efficiency on the other hand and make sure that doesn't fall below some threshold. So we're automatically seeking the lowest energy level possible. And what I'd say to kind of close out my answer before throwing it to Tom is, looking out on the horizon where we are at the close of the first quarter of the 21st century and seeing the rapidly evolving technological and regulatory landscape in front of us, it's just, like I started saying, it's just so exciting. And we're really excited to be part of the solution. Just one of the, in my opinion, the most important challenges facing us as a society, how to conserve what I consider to be our most precious resource that's currently in a condition of scarcity in some places in the country, out west and such, and turn that from scarcity into abundance so that we can leave that behind as a legacy for the next generation.
Great answer. Tom?
Well, so, one of the things is working at Mazzei, it's really a great experience to work alongside so many brilliant people, both on the engineering side and chemical process side, to do these tremendous innovations of the product as the market is continuing to challenge us for water reuse and the other applications that Erich mentioned. But I also want to tip my hat to our customers because, for instance, on one of our installations, that was a fine bubble diffusion to side stream retrofit. When the fine bubble diffusion system was put in place, they put in ORP meters to monitor the dissolved ozone residual, the impact of the ozone residual as kind of a window to select the ozone residual. And what they found is that downstream of the fine bubble diffuser was too variable. It wasn't able to make controlled decisions at all. When they put the side stream injection in, they continued that idea, even though it was 20 years later, to look at what ORP could possibly do. And in fact, because the signal stabilized, it did finally provide a window for them to determine what the ozone dosages need to be, even ahead of what they were from the dissolved ozone residual, provided a quicker response time. So there's things like that are occurring not only inside of Mazzei, but are occurring in the water industry itself, where people are continuing to optimize and improve performance of systems. And it is, like Erich mentioned, and is, Sannel, something very exciting to be part of.
Thank you so much. So once again, this has been a great conversation, great discussion on, I think, one of the most critical and often overlooked aspects of ozone system performance. Tom, Erich, thank you again for sharing your experience. And to everyone watching, if you want to learn more about ozone injection systems, on how Pinnacle integrates Mazzei technology into complete system, please feel free to reach out to pinnacleozone.com or mazzei.net. Again, thank you everyone for joining us at Pinnacle Academy, and we'll see you next time. Thank you.
Thanks, Sal. It's a pleasure speaking with you.